This is a video about solving systems of equations using the algebraic method substitution. When using substitution, we're trying to solve a system of equations not through graphing, but by using equations and solving for x or for y. The first step of substitution is to isolate any variable. So, looking at these two equations and looking at them very carefully, I notice that there's a variable that's already isolated. That would be my x. So, I have no work to do in order to isolate a variable. Now, I notice that x is the same thing as 3y plus 4. Looking at my other equation, I can therefore substitute the x in the other equation with the 3y plus 4. So I'm going to write my second equation, y plus, and then I'm going to include a set of parentheses in case I have to distribute, 3y plus 4, and then just finishing off my equation equals 16. So all that I really did is I took the x from the second equation and I replaced it with something that I know x is equal to. So that's why I have to isolate any variable first so that I can substitute. Once I've substituted, now it's just a question of solving my new equation. So this is really just y plus 3y plus 4 equals 16. This is just 4y plus 4 equals 16, 4y equals 12, and y equals 3. So I now know that in either of those equations, y equals 3 is part of my solution. So how do I find my x? Well, I take that y equals 3 and I substitute again. So after solving, I'm going to substitute again. And I can substitute into either of my original equations. So I'm looking at the top two equations, and I notice that the second one looks a little bit easier. So I'm going to substitute that y with a 3 plus x equals 16. I'll go ahead and solve this equation. So x equals 13. My solution then becomes 13, 3. Looking at the original equations, I can solve or I can check this solution by plugging in 13 for x and 3 for y. In the top equation, if I do that, I get 13 equals 3 times 3, which is 9, plus 4, which is 13. 13 equals 13, so that would be correct. Looking at the second equation, I would get 3 plus 13 equals 16. That is equally correct. Not only can I say that I have a solution to the system, but I can also classify this system as independent since there is one intersection point. So let's try that again. Now in this problem, I'm going to have to solve for one of my variables first. So looking at the two equations, I notice that there's a b in both of them. I notice that the top one has a positive b, so I think it's going to be really easy just to move that 2a over and get b equals negative 2a plus 3. So b is now by itself. Now I can substitute into the other equation. So I'm going to write that second equation, 4a minus, I have to include that negative there, parentheses, negative 2a plus 3, close parentheses, and then just finishing up the equation. So again, I'm just replacing that b. I'll have to distribute my negative now. So 4a negative times a negative 2 is plus 2a, minus 3 equals 3, 6a minus 3 equals 3, 6a equals 6, and I will get a equals 1. Now to find my b, I'll plug that into either of the equations. I can actually plug it into the top equation there. So 2 times 1 is 2, plus b equals 3. So solving for b, I can determine that b equals 1. So my solution is 1 comma 1. And checking those out, 2 plus 1, 2 plus 1 is 3, and 4 minus 1 is also 3. Again, I have another independent system. Let's try this one more time, just realizing that sometimes substitution can be just a little tricky and sometimes some strange things can happen. I'm going to look at my two equations. I identify that x almost by itself. So let's just move the 2y over. X equals 1 minus 2y. And now that I have x by itself, let's go ahead and substitute. So 2 parentheses, 1 minus 2y, close parentheses, minus 2 equals 4y. 2 minus 4y. I just realized that I had forgotten to put this negative up there, so I just placed it in there. So 2 minus 4y minus 2 equals negative 4y. Combining like terms, negative 4y equals negative 4y. Adding 4y to both sides, 0 equals 0. Ooh. Now this is a true statement. So what does that mean? Typically, that means that I have lots and lots and lots of solutions. In this case, it does mean that I have an infinite number of solutions, but it really means that these two equations are actually for the exact same line. So my intersection points, my solutions, just become all points on the line. And this would be an example of a dependent system. Anytime I have two equations that are actually the exact same line, that is a dependent system.